Now, one thing before I start the recording session, let me tell you something regarding this experiment. Um from the discussion part, um, everything will not be clear, right? Unless you perform this experiment in the laboratory, and you observe everything what is happening during the experiment, you'll not be able to appreciate the actual merit of the experiment. Now, the second point is the report which I managed to uh, collect is a very poorly written one. That is a problem. So I'll tell you which data are not correct, or but it's not possible for me to provide you the correct data. So, and another thing is, uh, at times, when we actually perform this experiment in lab, we get some erroneous data. What is the reason behind that? The reason behind that is the sensor diode will see that there is a sensor diode in this particular, which has been used in this particular experiment. That sensor diode often doesn't uh, give us give us an accurate measurement. That is one problem, and the performance of the sensor diode um, gets worse with aging. So that's why exact temperature, what should be the ideally what should be the temperature, that value often we don't get from the sensor diode. And the other problem is the chattering of the relay or relay switching. Again, with the aging of the relay doesn't switch at desirable instance. So that's why that is another source for erroneous reading or erroneous results. Right? So anyway, let's try to understand the basic theory behind this experiment. Okay? So you'll find that the results are not matching with the theory, but actually we are in a pretty helpless situation. Can you see the material?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
So the title of the experiment is Study of On-Off Control System, and the objective is to study the operation of a feedback on-off temperature control system. Now, the first thing is familiarization with the building blocks. So the first block that we are going to use is the input transducer. Why we will be requiring an input transducer? Because it's a temperature control system, on-off control system. That means, yeah, it's written over here, on-off temperature control system, right? So it's apparent that the output signal generated by the plant will be temperature. Now, with the help of input as well as output transducer, will convert. Uh, First, let me talk about the output transducer. So, the control signal generated by the plant will be the temperature, and that particular temperature will be converted into a voltage signal with the help of an output transducer. So since we are using one output transducer to convert this temperature to voltage signal, hence in the input end will be requiring the input transducer, which again will convert the temperature to be maintained, the temperature of the plant to be maintained at a fixed value to a voltage level or voltage value, right? So, what is the function of the input transducer? The reference or set point value of the temperature. Suppose we want to maintain the temperature of a particular plant at say 70 degree. So that is the reference or set point temperature value. We will convert this set point or reference temperature value to a voltage value with the help of this input transducer, and that is nothing but a simple potentiometer whose gain constant is zero point 0.1 volt per degree centigrade. So what is the meaning of this? That is, if I want to set the temperature at 70 degree, then I'll have to give an input to the entire system which is equal to 7 volt with the help of this potentiometer which is acting as an input transducer. Now the output transducer, so the temperature is actually measured by means of a small signal silicon diode. And we'll see that this sensor diode, we call it a sensor diode. It's a small signal silicon diode. Hello, am I audible?
Yes, ma'am. Yes, ma'am.
Okay.
Yes,
So
ma'am.
the small signal silicon diode, the sensor diode, and that will be our temperature sensor. Why? Because for such a diode, the forward voltage drop depends upon the temperature, which is y, and the relation is given by uy. This is the forward voltage drop, which is basically a function of temperature, and it's given by a minus by, right? So here in this experiment, the sensor diode that we'll be using, um, it's clear from this that a and b are constant. So the sensor that we'll be using in the laboratory have A and B this constant as 630 millivolt and 2 millivolt per degree centigrade, per degree centigrade. Okay, so these things are not that important. We don't have to memorize these constants anyway. But since this particular relation is not quite convenient to us, so along with the sensor diode, we'll be using a level shifter whose function will be to convert this expression into an expression which is given by c is equal to zero point y. So let's see, the output available from the sensor is passed through an amplifier cum level shifter so as to produce the feedback variable c in volt, right? That is, we are converting the output temperature into a volt, and the level shifter will change this relation to this relation, that is the output voltage generated by the level shifter, and this is related to the temperature of the plant by this relation. So c is 0, as you can see, c is zero point 0.1 into the temperature, output temperature y. So an example is given. So if the temperature of the plant is 73 degree centigrade, then the value of C, that means at the output of the level shifter will get a value voltage value which is equal to 7.3 volt. right? And one thing is clear, that is the gain of the input transducer, that was zero point 0.1 volt per degree, as well as the gain of the output transducer are same, and they're equal to zero point 0.1 degree centigrade. আর allow করা যাবে না. Okay. Now, before I come to the plant, let me show you the. Can you see this block? This is the amplifier plus level shifter block. So these are the inputs. This input is connected to the ground, and we have taken this input to the level shifter from the sensor diode, and the output of this amplifier and level shifter block is a voltage value which is proportional to the temperature of the plant measured by the sensor diode. Clear? And this aluminium block, can you see this block? This aluminium block is our plant, and the sensor diode is embedded with this in this particular plant, right? And from these two terminals, we are using uh, across these two terminals, we are getting the value of the output variable measured by the output transducer, which is a sensor diode, right? And we, in the closed loop, will feedback this voltage signal, and that will be the input to this level shifter, and at this point we'll get a voltage which is zero point 0.1 into y, where or yp, where yp is the temperature of the plant at any particular instant. Now the system or the plant. The system under study is a block of aluminium, as you have seen, that is heated by an embedded 65-watt electric heating element and cooled by a small 15-watt fan. And this is our basic assumption, that is, the block is assumed to have uniform temperature throughout its body. That means there will be no temperature gradient. Why we have assumed this? Because with the help of this assumption, we'll be able to derive the transfer function of the plant, right? Or rather, we can say that the plant can be assumed to be a linear one, only if this condition is satisfied. So if there is no temperature gradient, then we can approximate the plant as a linear one, and thereby we can find out its transfer function. So let me show you the heating element and the cooling element. So as you can see, this is the soldering iron, which will be used as a heater in this particular experiment. And this is the small fan which is available in the system of a typical desktop computers. So this small fan is the cooling element. Right? So when the soldering iron will get the power, it will act as a heater, and when the fan will get the power, it will act as a cooler. So accordingly, when the heater will be connected across the supply, the temperature of the plant will increase, and when the fan will be connected across the power, when the fan will get the power, the temperature of the plant will start decreasing. So we have discussed this. Now, when we'll operate the system in a closed loop, then we'll be requiring a summer or a subtractor that we know. That means the reference input R, from the reference input R, will have to subtract the control output C, right? And the error signal will drive the controller and the plant. Okay. So we'll be requiring an error detector, and in this experiment, we'll use a unity gain difference amplifier as an error detector, and the output of the difference amplifier E, that is the error signal, will be equal to R minus C, where R is the reference input and C is the control output. So this is the diagram, or rather this is the figure of this block. So you can see the potentiometer or schematic diagram of a potentiometer, right? So this is our input transducer. With the help of this knob, we can change the position of this particular jockey, and accordingly we can get a desired voltage at the output at this point, right? So this is our reference input, and this reference input is connected. This voltage signal is applied to the non-inverting terminal. This is a plus one non-inverting terminal of this difference amplifier. And when the system will be operated in a closed loop, now you can see that the other terminal of this difference amplifier is basically grounded, right? So this terminal will be grounded when we'll operate the system in open loop configuration. And if you want to operate the system in a closed loop configuration, this is our reference input R, one input to this difference amplifier, and the second input, instead of connecting this to ground, now we'll have to connect this to this point, right? So at this point we are getting the signal C. So at this point we'll get the signal C, voltage signal C. This is our input voltage or reference input voltage R. So at the output of the difference amplifier we'll get the error signal E. What's going on? So at this point, we'll get the error signal. And as you can see in this diagram that this error voltage is now being input to a nonlinear element, which is level dash Schmidt trigger. It's basically a hysteresis block, a nonlinear element, and the output of the hysteresis block or the Schmidt trigger is connected to an electromagnetic relay. And here are two sockets, as you can see. One is dedicated for fan and the other one is dedicated for heater. So in when we'll be connecting, or when the system will be uh, operating in closed loop mode, then both the sockets will be required. The heater plug, can you see these two plugs? One is the heater plug, the other one is the fan plug. So the heater plug will be connected to this particular socket, and the fan plug will be connected in this particular socket. So I'll come to the closed loop operation later on. First of all, let's try to understand how the system will behave in open loop. So for the time being, I'm not discussing the Schmidt trigger or Schmidt trigger characteristics, etc. But this thing will be required. Okay, fine. So the error signal, if the error signal is passed through a Schmidt trigger, we know that the Schmidt trigger does have an output which is a Boolean variable. Have you studied Schmidt trigger in electronics?
Yes.
You are supposed to. So the output of the Schmidt trigger, that is H on, will be equal to 1 if the error signal is greater than equal to a value, pre-specified value E, right? Which is constant. And the output of the Schmidt trigger will be 0 if the error signal is less than equal to E, equal sign is less than equal to E, right? So this E is a potentiometer adjustable threshold of the Schmidt trigger. The value of plus E and minus E are also termed as the upper trigger point and lower trigger point. Why these two values are called trigger points? Because when if E is just equal to capital E, then the H on value will be 1, right? And otherwise the H on value will be 0, right? So when we'll be studying the transfer characteristics of the Schmidt trigger, we'll see that at minus C there will be a transition from 0 to 1. Transition of which? Transition of the output of the Schmidt trigger. And it will change from 0 to 1, and at plus C it will change from 1 to 0 or vice versa, depending upon the transfer characteristics of the Schmidt trigger, right? So that's why this plus C and minus C are termed as upper trigger point and lower trigger point. At these 2 points, the output value of the Schmidt trigger will change. And also we note that for E in the band minus C to plus C, if E lies between minus C to plus C, H on may be 0 or 1. H on may be 0 or 1 depending on its previous state, right? So if H1 was 1, then in the next instant, in the next instant, H1 will remain 1 if E lies within this particular range, and vice versa. So this band gap 2E, that is E minus minus C, is called the hysteresis band. Now, after this mid trigger, we have seen that there is an electromagnetic relay. You see the circle? This is the electromagnetic relay, and when the electromagnetic relay will be energized, so this um, light will be on, right? And when the electromagnetic relay will be de-energized, this will now be off. So when H on is 1, then the electromagnetic relay will be energized. On the other hand, if H on is equal to 0, then the electromagnetic relay will be de-energized. Moreover, if the electromagnetic relay is energized, the heater will be on. And when the electromagnetic relay will remain de-energized, during that period the fan will be on. Fan will get connected in the circuit and it will be on. So the heater and the fan will be so connected that for H on is equal to 1, the heater will be connected to its rated supply, and for H on is equal to 0, the fan will be connected, whereas the heater will remain off. So circuit diagram. So this is the complete arrangement, complete setup. Have you studied electromagnetic relay?
No, ma'am.
So, what is an electromagnetic relay? We were claiming that if H on is equal to 1, the electromagnetic relay will be on and the heater will be connected in the circuit, right? And when H on is equal to 0, the electromagnetic relay will be de-energized and hence the the heater will be cut off from the circuit and fan will get connected in the circuit. So what is the basic principle of operation? An electromagnetic relay basically consists of an electromagnet, right? And there is one movable armature along with that particular electromagnetic or electromagnet. So let's, for the time being, since we don't have any diagram right at this point of time, let's assume that we have an electromagnet, and this is the armature which can move. Okay, so when the coil of the electromagnet will get supplied, so the electromagnet will be energized, right? And when the electromagnet will be energized, it will attract this movable link or the armature. Am I clear? So it will attract that movable link or the armature towards itself. And what will happen, you see, when the relay was de-energized, this movable contact was connecting this point to this point, right? So if we give supply to this and if you connect the fan in this particular socket, the plug of the fan in this particular socket, then when the relay is de-energized, the fan will get the rated supply and it will be connected in the circuit. Now, when the relay will get energized, this contact will be broken. Why? Because the coil will now attract this movable link or the armature towards itself. Hence, this contact will be broken, and now the power is such that the link will move to this particular point. Am I clear? Hence, this contact will be now made and this contact will be broken. So, what will happen? Finally, the fan will be get disconnected from the circuit, and since now this contact is closed, and this contact is open, hence the heater will get this is our phase. So the heater will get connected across the phase and the heater will get the rated supply and heater will be connected in the circuit. Have you understood this?
Yes, ma'am.
So you see, when the relay is de-energized, this contact is closed. Hence, we call this type of contacts as normally closed contacts, right? And this contact is open. Relays are associated relays to have electromagnets as well as several contacts like this. Some of the contacts are normally open and some of the contacts are normally closed. So you see, when the relay is de-energized, this contact is closed. Hence, this contact will be said to be a normally closed contact. Whereas this contact is open, and hence this contact will be called a normally open contact. So in short, we represent the contacts as NO or NC. NO means normally open and NC means normally closed, right? So the condition of the contacts when the relay is de-energized. Based on that, we classify the contacts as normally closed and normally open. And whenever the relay will be energized, the state of the contacts will change. So the normally closed will become now normally open, and the normally open one will now become normally closed. Do you have any question?
No, ma'am.
So this is the circuit diagram. So in the for when the system will be operated in closed loop, as I said, the output of the amplifier and level shifter will be the second input to this difference amplifier. Now first we'll study the system when the system configuration is an open loop configuration. So what is the procedure? This is run one. Disconnect the heater and the fan plugs from their respective sockets. Fine. We have disconnected. Turn on the AC supply. Measure and record the value of the AC supply voltage V or VAC. Right? Why it will be required? It will be required for measuring. Let me come to this point, for measuring the steady state temperature rise above ambient. So first of all, we'll have to measure the ambient temperature. Then, after measuring the AC supply voltage, we'll have to measure the steady state temperature rise ZSS above ambient. And the empirical formula is ZSS is equal to 0.00225 volt VAC square. This V and VAC. VAC square. There are several typos in your instruction sheet. You will find that in the instruction sheet it's written that we are using two sensor diodes. No, it's not correct. We are using one single sensor diode. Okay. So connect the non-inverting input where to the reference port. Already we have seen the connection. Inverting input to the ground. Yes, we have seen that. And the output of the difference amplifier to the of the Schmidt trigger. Input of the Schmidt trigger, right? Now we have not adjusted the band, that is 2E, the hysteresis band of the Schmidt trigger. So in the open loop mode, actually Schmidt trigger is not playing its role. Schmidt trigger will play its role in the closed loop while the system will be operating in closed loop mode. Now connect the sensor diode to the sensor amplifier, observing the proper polarity that we have done. We have connected the sensor diode. Yes, we have connected the sensor diode to the sensor amplifier, right? And we have connected the reference input to this terminal. This terminal has been grounded. The output has been connected to the Schmidt trigger. We have not adjusted this band, right? So this is, and we have not yet connected either the fan or the heater. So we have measured the steady state temperature rise above ambient. And how to get the ambient temperature? Just measure the value of C. You have not connected the heater, you have not connected the fan, right? Just at that condition, in that particular condition, measure the value of C, and the value of C will give you the ambient temperature. Do you get my point? Is it clear?
Yes, ma'am. Yes.
So that's we are measuring the ambient temperature. Next, what we'll have to do? Okay, now we are adjusting, this is important, the value of R to 1 volt, right? Now, since as I said, the system is operating in open loop, the other terminal of the difference amplifier or the error detector is grounded. That means C is not being fed back, right? So that means the error voltage E is always, which is R minus C, is always positive, right? So what will happen? That is, so now we'll insert the heater plug in its socket and we'll consider this instant as time t equal to 0, right? And measure the value. Yes, as I said, now R minus C error voltage is positive, so the relay should now be energized. So that LED will glow. Okay. So relay will be energized. That means relay is energized. That means now next we have connected or we have put the heater plug into its socket, and since the relay is energized, now this contact is closed. That means the heater is now connected in the circuit, whereas the fan is cut off. Clear? So we'll have to insert the heater plug in its socket and consider this instant as time t equal to 0. Then we'll have to measure the value of the sensor amplifier output C at intervals of 1 minute up to 15 minutes. We'll have to record the values of times S, the symbols are a bit peculiar anyway, values of times S, CV, that means the temperature of the plant. We are not trying to, since the system is operating in open loop, that means we are not trying to control the temperature of the plant right now. Only we are observing the temperature rise. We are studying the system. So what is the output temperature or what is the temperature of the plant? And temperature rise above ambient, that is Z, which is equal to Y minus YA. Y is the ambient temperature that already we have computed. So plot Z as a function of time on a graph paper and find the value of the heating time constant. So here you can see that this is the value of C, hmm, and from that value of C we have calculated the ambient temperature as 20.5 degrees centigrade. Now using this value and taking 63.2% of that, that means for calculating the time constant, we have calculated the uh, temperature rise above ambient. That means we'll have to raise the temperature of the plant at least up to this value, otherwise we'll not be able to calculate the heating time constant. And this is the table, and the table is not that significant to you because only these are some values, but one thing is clear, you see, since the heater is now connected in the circuit, so the temperature will start rising from the ambient one, and yes, it's rising. And here the final value of the temperature that we can observe is they have got this result, that is 95.2 degrees centigrade. So this is the heating process and temperature, and this will give us the last column will give us the temperature rise above ambient. So this is the plot. The plot is not very properly drawn, Anyway, uh, I guess now you can see the plot. This is the heating process from. Can you see this one? Temperature rise above ambient. Ambient was 20 degrees, so temperature rise above ambient means the graph will start from 0 0 degree, and this is the heating process. And from this plot we'll have to find out, you can see that it's an exponential rise, so from this plot we'll have to find out the heating time constant. Next, can you see this? Is it legible?
Yes,
Yes, ma'am.
So next what we'll have to do, after 15 minutes, what we'll do, we'll just remove the heater plug from its socket and put the fan plug in the same socket. That means in this heater socket only, right? So we'll remove the heater plug from the socket and put the fan plug in the same socket as quickly as possible. Why? Because you see at this particular point, we will be getting the supply. So that's why we are connecting the fan in this particular socket, and we are taking off the plug of the heater. That means now relay is energized, so this points are connected, this contact is made, so that's why now the fan will be connected in the circuit and heater will be off. So now the cooling will take place. So again, remove the heater plug from its socket and put the fan plug in the same socket as quickly as possible. Taking this instant as t equal to 0, take recordings of Z versus T graph at 30-second intervals up to 6 minutes. And then we'll have to plot Z versus T, and from the plot itself we'll have to find out the cooling time constant. These are the values, and since now the fan is connected in the circuit, the temperature will now start decreasing. So 95.22 is quite illegible, at least for me. Yes, this is 83.75 degrees, so temperature is decreasing, and this is the temperature above ambient. So this particular plot has been incorrectly drawn, right? Actually we are supposed to plot two separate, we'll have to draw two separate graphs, one for heating and the second one, a second graph paper will be required for plotting this cooling curve. And remember, this time should be considered to be time t equal to 0. Anyway, from this plot also we can find out the cooling time constant if we can consider this time to be time t equal to 0. And you know how to find out, this is exponential rise, exponential decay. From the nature it's clear, nature of the plot. So you know how to find out the cooling time constant and heating time constant. Now run 3 and 4. So what we'll have to do now, we'll have to switch off the AC supply. Now we'll connect the system or configure the system in a closed loop mode, right? And if you perform the experiment, then you'll see that automatically at one point of time the heater is being connected in the circuit, and at some other point of time automatically the fan is getting connected to the circuit, right? So it's a closed loop configuration and no manual intervention will be required. You don't have to put the plug into the socket or the heater plug in the socket. It's not required. So it will be an automatic operation in the closed loop configuration. So we'll have to switch out the supply and take out the fan plug from the heater socket. We'll have to Now we'll have to adjust the hysteresis adjustment port in position A, which corresponds to an E of 200 millivolt. Right? So we'll have to connect the non-inverting input to the reference input that we know. Now we'll have to connect the inverting input to the sensor amplifier output C, and the output. So the two inputs will be connected, one to the reference input, other to the controlled output, right? So that means we are connecting the system, configuring the system in closed loop mode. Connect the Schmidt trigger input to the output of the difference amplifier, switch on the AC supply and adjust R to 7 volt. R is equal to 7 volt means now we want to maintain the temperature of the plant at 70 degree. 7 into 10. So now we want to maintain the temperature of the plant. Now we are actually controlling the temperature of the plant, and this basically a set point or uh, regulatory kind of problem. I have discussed what is a regulatory kind of problem and what is a tracking kind of a problem in theory class. So there's a regulatory kind of problem. So actually we want to maintain the temperature of the plant at 70 degree centigrade. But we have one Schmidt trigger in the circuit. Now switch off the AC supply and insert the heater and the fan plugs to their respective sockets. So now we'll connect the heater into the heater plug in the heater socket and the fan plug in the fan socket. So connect the voltmeter to the C output so that we can measure this value C, and switch on the AC supply at time t equal to 0. The closed loop on-off control system is operational now. So how the closed loop system will operate? For that now we'll have to look at the transfer characteristics of the Schmidt trigger. So I'm explaining using this diagram. This Schmidt trigger part is not clear from this. But one thing you can say, there is a potentiometer and this is a knob. With the help of this knob, the potentiometer can be put either in this position or in this position, position A and position B. So position A will give you a hysteresis band which is equal to 400 millivolt. That means 200 millivolt into 2. So plus E is equal to 200 millivolt, minus E is equal to minus 200 millivolt, and hence 2E, the band is the bandwidth is actually the width of the band, not bandwidth. The width of the band is equal to 400 millivolt. And if we put the potentiometer at this particular position B, then E value will be equal to 500 millivolt minus E minus 500 millivolt, and hence the width of the band will now be equal to 1000 millivolt. So if I connect this, if I put the potentiometer at this particular position, 200 millivolt, that means 2 degree of excursion in this direction about this point, and minus 2 degree of excursion in this direction about this point. Am I clear?
Yes, ma'am. Yes, ma'am.
So let's refer this particular figure. Okay. Don't go by this arrow directions. So the reference temperature is 70 degrees centigrade. So this is the mean temperature, which is 70 degrees centigrade, right? Now, since this plus E value is 2 degrees centigrade and minus E value is minus 2 degrees centigrade, hence, what will happen actually? The temperature will start increasing. We'll have to see where in the previous run what was the temperature anyway. So the temperature was pretty less. So now the reference temperature is 70 degrees centigrade. So temperature will start increasing. Let me check the value. In the last run, the temperature was 31.5 degrees centigrade. Uh, 31.5 degrees centigrade, right? Now heater is off. Sorry, fan is off and the heater is off. So we can assume, okay, the temperature will be around 31.5 degrees centigrade. Now, since the reference temperature is 70 degrees centigrade, so the temperature will start increasing, right? Now, because of the presence of this Schmidt trigger, this nonlinear element, the temperature will go on increasing beyond this value 70 degree, and the temperature will go on increasing up to a value which is equal to ideally up to a value which is equal to 72 degrees centigrade, right? That means the error voltage E R minus C is equal to minus 2, right? And which is greater than the voltage value, or greater than or equal to E, right? So now what will happen? The heater will be off. The heater will be off and the fan will be connected, or the output of the Schmidt trigger H1 will switch from 1 to 0, and the fan will be connected in the circuit, and the temperature of the plant will start decreasing again. So far, is this clear?
Yes, ma'am.
So how long it will decrease? Ideally, when the temperature will reach a value which is equal to 68 degree. That means 72 minus 2. 68 degree. At that point, the difference, or if it's slightly below that value, so you see the temperature, or the error value E, R minus C is less than E, less than equal to E. Again, at this trigger point, the output of the Schmidt trigger will change. So from this point to this point, the fan was connected in the circuit since the relay was de-energized as H1 is 0. Now at this point, when the temperature is 68 degree, again the H-on. H-on value will switch from 0 to 1, and now the fan will be disconnected from the circuit and the heater will be connected to the circuit. So the temperature will start increasing again from 68, ideally from 68, and it will go on increasing up to 70 degrees centigrade. Again, the heater will be off, fan will be on. So this cycle will continue. Have you understood? This is actually the basic control essence of this experiment, on off control. Once the heater is on, at other time, at some other point of uh, other time instant, the heater is on off, right? Or we can think about H on. So 1010, or even we can think of the relay. Relay is switching. Either the relay is getting energized or the relay is getting de-energized. That's why the name of the experiment, or typically we call this kind of control scheme as on-off control scheme. And here, since we are trying to control the temperature of a plant, hence the name of the experiment is on-off temperature control system. So why are we using this Schmidt trigger? Why we are deliberately introducing this nonlinear element in the circuit to reduce the chattering of the relay, right? So, if the Schmidt trigger is not present, then what will happen? If the temperature reaches the relay characteristics will be like this, like this. সপ্তর্ষি আছো?
Ma'am, oh, section B.
সেকশন এর কারা আছো ননলিনিয়ার অপটিমাল কন্ট্রোলে? সেকশন এ থেকে
Yes, ma'am.
শুভ শুভশ্রী ঐশানী দেখলাম তো সেকশন এ তো।
ম্যাম আমিও আছি।
আমিওটা কে নাম?
ম্যাম সায়ন সায়ন।
সায়ন, হ্যাঁ মনে পড়ছে। অন অফ কন্ট্রোল সিস্টেম, রিলে সুইচিং। প্লিজ রেসপন্ড। নন লিনিয়ার কন্ট্রোল যারা পড়েছো তাদের অন অফ কন্ট্রোল সিস্টেম মনে পড়ছে? ব্যাং ব্যাং কন্ট্রোল।
না ম্যাম ঠিক
সে কি?
মনে পড়ছে।
আমরা মিনিমাম টাইম ট্রাজেক্টরি রিলে সুইচিং পড়েছি তো। যখন ফেস প্লেন অ্যানালিসিস করেছি। Classic. Anyway, the ideal relay characteristics is like this. So whenever the temperature will be 70 degree, the relay will be on. Whenever the temperature will be slightly below 70 degree, the sorry, the relay will be on, and whenever the temperature is slightly above 70 degree, the relay will be off, and the fan will be connected or the heater will be connected, right? So the switching operation or switching frequency of relay will increase. And what is the problem with that? If the switching frequency of relay increases, then the life of the relay decreases rapidly. That is the problem. So to reduce the chatter of the relay, that means on off or switching of the relay, deliberately we introduce a Schmidt trigger having this kind of dead band so that the relay will not change its state at this very instant. Rather, the chattering time will vary from this point to this point. Am I clear?
Yes, ma'am. Yes, ma'am.
So, what is the procedure? Do not take any reading when we have connected both the heater and the fan at their respective sockets. That particular time we are considering to be time equal to 0. Now, we are not taking any readings now, but we are trying to accurately record the time at which the relay is de-energized. Relay is de-energized means H on is equal to 0 and fan will be open. That means the temperature will start rising from say 31 or 32 degrees centigrade to up to 72 degrees centigrade. Ideally up to 72 degrees centigrade, right? And then the relay will be ideally de-energized and the fan will be connected and the temperature will start decreasing and will get lower at a value which should be ideally 68 degree. So we are noting that particular time, and from that instant we are supposed to take readings of C. That means the temperature of the plant, which we try to control at every 20 seconds for 3 minutes. And after doing this, again we'll have to complete another table which is run 4. The steady state operation has been reached by now Note the relay on time, how long the relay is remaining on, that relay on time T1, and off time, how long the relay is remaining off. Relay on time means the heater is connected in the circuit, and relay off time means the fan is connected in the circuit. And those two will be automatically connected. I guess that you can appreciate. So, and the maximum temperature by age. So relay on time, that means the heater is in the circuit, and at the end of relay on time, we are supposed to get the maximum temperature of the plant, isn't it?
Yes.
And at the end of this relay of time, so fan was connected and the cooling was taking place, and at the end of that time we are supposed to get the minimum temperature of or temperature of the plant, which is the minimum, which is at the minimum value respectively. But if you, this circuit is incorrect, heater and time, heater and fan, they are connected to the supply through this two contacts, but both the contacts cannot be normally open, right? So this is the symbol for a normally open contact, and if I cross the normally open contact in this manner, then that particular notation is used to represent a normally closed contact. So this is the reading, and you see, ideally the maximum value would have been 72 degree, right? But here we are getting 75 degree. That means the relay has not switched at the right instant, which is 72 degree. That would be the problem of the relay. That would be uh, the measurement error of the that measurement error uh, that or measurement error of the sensor generated by the sensor, right? The sensor should have shown 72 degree, but instead it's showing 75 degree. So these readings are not really. And here you see the table is also not correct. The heater on time, after heater on time, the second column should have been the maximum temperature. And heater off time, after that, we should record the minimum temperature. Anyway, so heater on time 62 degree, and we are getting a temperature which is 75 degree. So for 200 millivolt, uh, half hysteresis band, this should not be the value. Anyway, if you can understand the basic principle of operation of the control scheme, that would be sufficient. Now, observe the polarity of error. This is run 5. Observe the polarity of error is indeed reversing cyclically under this condition. Record the maximum and minimum values of voltage error and temperature error. This phenomenon, frequently observed in on-off control system, is termed as limit cycle oscillation in nonlinear control theory. The linear system cannot exhibit limit cycle oscillation, but some nonlinear system can exhibit limit cycle oscillations, right? And this on-off kind of nature is basically what is limit cycle. Limit cycle oscillation is nothing but a self-sustained oscillation, a self-sustained oscillation with fixed amplitude and fixed frequency. Nonlinear control স্পেশাল পেপার যাদের লিমিট সাইকেল শুনেছো না সেটাও শোনোনি?
Yes, ma'am.
বন্ধুদের explain করে দেবে what is limit cycle oscillation, right? Now the problem is, first of all, they have taken wrong data. Let me find out. This is the minimum time, maximum time. Yeah, they have taken wrong data. Calculated value, measured value, error, MV minus CV. I don't know. So this should not be the table. So the first column should be the minimum actual value. The second one should be the reference value. And the third column is the error. So calculated uh, here we are not calculating any values. We are just observing. We are recording the temperature of the plant, right? So calculated, this term should not be used over here. Anyway, in ideal case, would have been the minimum temperature of the plant in this particular situation with this statement should have been 68, 68, and 68, ideally. And what is the set value or reference value? That is R. Error means R minus C. So this is C, this is small r. So R value is 70 degrees centigrade, 70 degrees centigrade, 70 degrees centigrade. So this is fixed. This we have set. This values, this temperature values, we are measuring with the help of the sensor diode, right? And ideally, I can assume that this value should be around 68, 68 degrees centigrade. Could be 67.5, it could be 68.1, something like this. Once we calculate the error values, then the error value will be here 70 minus 68, R minus C, which is 2. Here 70 minus 68 plus 2. Here 70 minus 68 plus 2. Now, let's come to this point. Again, this is the recorded value of the plant, and ideally should be 72, 72, 72. It could be 72.5 in real time. It could be 72.5. It could be 72.7. It could be 72 or 71.9, but should be around 72, right? And the set values are constant, that is 70, 70, 70. So what will now be the error? The error value will be R minus C. So it will be minus 2, around minus 2. It will be around minus 2. It will be around minus 2. Have you understood this?
Yes, ma'am.
Yes, ma'am.
So that's why we are not getting the pattern in this particular table. So what is written in that particular? So if you observe the error value R minus C, we'll find that the polarity of error is indeed reversing cyclically, right? Under this condition, plus 2, minus 2, plus 2, minus 2, plus 2, minus 2. And we can record the maximum and minimum values like 68 degree and 72 degree, etc. Right? And this cyclically varying, periodically varying error value from positive to negative actually results in a limit cycle oscillation in nonlinear system. Because of the presence of the Schmidt trigger, because of the arrangement, the error value, ideally the error value cannot exceed 72 degree and cannot be less than 68 degrees. So ideally the error value will vary, or the temperature of the plant rather, the temperature of the plant, not the error value, sorry, the temperature of the plant will vary from 68 to 72. That means the heating process will take place and the temperature of the plant will rise from 68 to 72. Then the fan will be connected, heater will be off, and the cooling process will take place, and the temperature will get lowered from 72 degree to 68 degree. and continuously this cyclical pattern will be maintained or can be observed in the system. Now, the next run is similar to this one, only we are changing the position of the potentiometer associated with the Schmidt trigger, and now the error value becomes 500 volt, 500 millivolt. That means the temperature excursion around 70 degree will be from 75 degree to 65 degree. Clear? So the same readings will have to be taken. Now this part is, so I'm not showing this one. So here only, as I said, the heating process will take place from ideally from 65 to 75 degree. Just we have increased the hysteresis band, and the cooling process will take place from 75 degree to 65 degree. Now what we are decreasing? We are decreasing the reference input to 5 degree, 5 volt. That means now the temperature of the plant should be maintained around 50 degrees centigrade. So consider this time to be equal to 0. Remember that the hysteresis band adjustment port is kept in position B, where the for which the E value is 500 millivolt, right? So now the reference, we have changed the reference to 50 degree. So now the temperature excursion will be from 45 degree to 55 degree, and then again back to 45 degree, then again the temperature will rise to 55 degree. So far, is this clear?
Yes, ma'am.
Yes.
Okay. So we'll observe that pattern. So somewhat a better result. 77 instead of 75, we are getting 77. Okay. And instead of 65, we are getting, the best result is 66.8. Anyway, now in the report, you will find for this run 5, the last run, in the report, we are supposed to draw the corresponding plot. Now, in the report, they have drawn this, mm, he or she has drawn this particular plot, which is completely incorrect. So, don't go by this plot. And there is no association between the cooling process, this is supposedly the cooling process, this is the heating process, with heater on time and heater off time. Just don't look at this particular graph. Instead, the last run will be, though it's also a very poor graph because I can't draw an exponential curve. So suppose when the time t equal to 0 and we change the reference input to uh, 5 volt, 5 volt, suppose at that particular time t equal to 0, the temperature of the plant was 73 degrees centigrade. Now since the reference input is 5 volt, that means the temperature of the plant should be 50 degrees centigrade, hence the fan will be on. So the temperature will start decreasing from 73, and it will go on decreasing, but it will be an exponential one, right? As we have seen in the heating curve and cooling curve, right? And it will reach 45 degree. Why? Ideally 50 minus 5 degree. So 45 degree. Now at this point, now the heater will be on, the relay will be energized and the heater will be on. So temperature will start increasing up to 55 degree ideally. Then again the fan will be on and heater will be off. So temperature will decrease. So you see within this band we are getting a sustained oscillation with constant frequency. Though it's not that apparent from this drawing anyway. So, but humans, sustained oscillation with constant amplitude and constant frequency. So, is the plot clear?
Yes, ma'am.
Yes, ma'am.
So, this thing I'm not discussing. You can go through this, go through the derivation. That means you'll have to find out the transfer function of the plant that I'm not explaining. I guess exponential rise and decay, and hence the plant has been modeled as a first order. This is the plant transfer function which they have obtained. You can see that it's a first order linear system. So I think this part will be legible. I'll send you the material. So try to find out, go through this and try to find out the transfer function of the plant. Ignore this plot. This is the end. So if you do have any question, we can discuss. Do you have any question?
No, ma'am.
So then should I end this session?
Yes, ma'am.
So could you gather any insight about an on-off control system? How an on-off control system operate in closed loop configuration?
Yes, ma'am.
I mean,